the Sun, a colossal sphere of fire that has illuminated life on Earth for 4.57 billion years. Yet deep within it still lie secrets that science has never truly touched. When the Daniel K. Inouye Solar Telescope and the Solar Dynamics Observatory delivered their first EUV 19.3 nanometer data, we reached into the deepest layers of the corona, burning at nearly 1 million Kelvin. For the first time, enormous plasma loops and vast coronal holes emerged, blasting high-speed solar wind directly into interplanetary space. It is also the realm where solar flares erupt at temperatures of up to 20 million Kelvin. Moments when magnetic fields reconnect and tear apart every notion of stability we once believed in. For the first time in history, we are about to witness the deepest region of the Sun, where it becomes its most chaotic. Prepare yourself, because to understand the fate of Earth, we must dare to look into the very heart of the star that created us. When we observe the Sun, there are moments when this star becomes completely unpredictable, unleashing eruptions on such a massive scale that they could bring all of modern civilization to collapse in an instant. That is when the Sun produces a coronal mass ejection, or CME. A release of energy and matter among the most powerful phenomena ever recorded in the solar system. According to NASA and ESA, a single CME can carry plasma equal to the mass of a mountain range, hurled into space at speeds typically between 400 and 2,000 kilometers per second. The most extreme events ever documented have exceeded 3,000 kilometers per second. But what is even more terrifying is that a CME does not need to physically strike Earth to trigger catastrophe. When the Sun's magnetic field twists and suddenly releases, that magnetic structure can be launched directly toward our planet and disrupt the magnetosphere. In such moments, it is not humans who are attacked. It is the systems we rely on to run modern society: GPS, fiber optic internet, satellites, power grids, aviation communications, and the entire telecommunications infrastructure. The Carrington event of 1859 remains the clearest example of this destructive potential. Historical data shows that electrical currents in telegraph lines became so strong they caused equipment to catch fire, even when unplugged. Auroras appeared as far south as the Caribbean, revealing a magnetosphere in unprecedented turmoil. What makes coronal mass ejection dangerous is not just their strength, but their unpredictability. They can form when filaments, vast ribbons of plasma suspended above the solar surface, collapse. These filaments often stretch hundreds of thousands of kilometers, some even surpassing Earth's diameter. When their magnetic support becomes unstable, the entire structure can fall inward and trigger an X-class eruption. According to research from SDO and the Solar and Heliospheric Observatory, or SOHO, X-class CMEs are the most powerful events that occur during the Sun's activity cycle, often accompanied by intense solar flares with plasma temperatures that can reach 20 million Kelvin. The data returned by Parker marked a turning point. Inside a CME is not a chaotic cloud, but a layered structure of intertwined plasma regions, overlapping shock waves, and magnetic field lines bent and folded like ribbons. Parker recorded the presence of switchbacks, reversals in solar wind direction, revealing that the Sun's magnetic field is not simply streaming outward, but kinked and folded, as if the star itself were shuddering from within. These observations allow us to better understand how CMEs propagate through interplanetary space. As a CME expands, it sweeps up everything in its path: cosmic dust, plasma, magnetic waves, and applies immense pressure to Earth's magnetosphere upon impact. Such an event once damaged transformers in Quebec in 1989, causing a massive blackout in just 90 seconds. In many forecasting models, NASA emphasizes that the strongest CMEs occur more frequently as the Sun approaches the peak of its 11-year activity cycle. Data from 2023 to 2024 shows that solar cycle 25 is stronger than expected, with flares and CMEs rising sharply, meaning the risk to Earth is increasing as well. And from the chaotic regions where CMEs are born, an even deeper mystery emerges. Why is the corona, the Sun's outer atmosphere, hundreds of times hotter than the surface? Why does plasma thousands of kilometers above the Sun reach 1 million Kelvin, while the photosphere sits at only about 5,700 Kelvin? It is a paradox that has persisted for 80 years, challenging even the foundations of modern plasma physics. Among all the paradoxes nature presents, the photosphere, the glowing layer visible to the human eye, sits at only about 5,700 Kelvin, a temperature that fits our expectations of a star. The farther you move from the core, the cooler things should become. But the reality is far more brutal. The corona above it can reach 1 million Kelvin. And in highly active regions, temperatures climb to 2-3 million Kelvin. This paradox is known as the coronal heating problem. First identified in the 1940s when scientists analyzed ultraviolet radiation from the sun. Since that discovery, for more than 80 years, telescopes, satellites, and mathematical models have tried to uncover what mechanism could possibly drive the temperature to such absurd extremes. In recent years, the most significant progress has come from the Daniel K. Inouye Solar Telescope, or DKIST. In 2024, DKIST captured ultra-small plasma threads moving with high velocities and constant variation, revealing magnetic interactions occurring on scales far smaller than previously predicted. Within these microscopic structures, many researchers see a potential explanation for the corona's extreme heat. Nanoflares. A single nanoflare is insignificant, but if billions of such explosions occur across the sun every second, the cumulative energy could be enough to sustain the corona at millions of degrees. Beyond nanoflares, another major hypothesis centers on Alphean waves, magnetic oscillations traveling along field lines within plasma. Observations from SDO, Inouye, and later IRIS showed that these waves can carry enormous energy and propagate at high speeds, sometimes reaching hundreds of kilometers per second. If these waves travel upward into the corona and release energy through their interaction with plasma, they may serve as an additional heating mechanism. However, the largest obstacle to this model lies in energy dissipation. In most simulations, Alphean waves pass through the corona without losing much energy, making it difficult for them to fully explain the extreme temperatures. But with new data from DKIST showing these waves becoming distorted, twisted, and dissipated within chaotic plasma, this hypothesis is gradually emerging as an essential piece of the puzzle. From a broader perspective, what unfolds in the corona may be evidence of a kind of magnetic turbulence that modern plasma physics has yet to fully describe. Massive magnetic loops stretching hundreds of thousands of kilometers. Plasma strands thinner than a human hair, yet longer than Earth's diameter. And regions of magnetic reconnection unfolding in mere milliseconds. All point to the idea that the corona is not simply the outer atmosphere of the sun, but an intricate energy ecosystem where classical physical laws struggle to provide complete answers. What is even more thought-provoking is that this paradox forces us to reconsider our place in the universe. Humanity lives under the light of a star whose internal workings remain beyond our understanding. And then, from this thermal mystery, an even more astonishing truth emerges. The light we use to study the sun is not even light from the present. It is light that remained trapped inside the star for 10,000 to 170,000 years before escaping. In the core of the sun, where temperatures reach nearly 15 million Kelvin, and the density is dozens of times higher than steel. Nuclear fusion reactions merge hydrogen into helium. This is where the very first photons are born. But there is one fact that human intuition never accepts easily. These primordial photons cannot escape immediately. And instead of flying straight from the core to the surface in a matter of seconds, as we often imagine, they are trapped in plasma so dense that each step they take spans only a few millimeters before being absorbed and re-emitted by another particle. This process, known as random walk diffusion, turns a photon's journey into a maze so intricate that there is no shortcut. Because of this, light requires anywhere from 10,000 to 170,000 years to move through the radiative and convective zones before reaching the photosphere. These numbers are not guesses, they are values confirmed by standard stellar structure models used by NASA. Based on the density, temperature, and opacity of the sun's plasma. We often say that sunlight reaches Earth in 8 minutes and 20 seconds, and that is true, but only for the final leg of a photon's journey after escaping the outermost layer. A photon spends almost its entire life in the darkness of the star before it is finally released into space. This creates a consequence more philosophical than scientific. No one is seeing the sun as it is. We only see the surface layer from which the last photons can escape. When a photon finally escapes the photosphere, it carries incredibly delicate information. The surface temperature patterns, turbulent ridges, magnetic signatures, the brightness of sunspots, the twist of active regions. It is this light that allows SOHO to map surface flows, SDO to reconstruct the sun's three-dimensional magnetic field, and the Parker Solar Probe to determine the strength of the solar wind. Are there deep internal changes unfolding that we have never detected? Is the sun's core experiencing oscillations that light can never reveal to us? Returning to the light itself, it carries a quieter message. Our existence depends on the past far more than we realize. Earth lives by ancient light. Plants photosynthesize using ancient light. Ecosystems run on cycles defined by ancient light. And every piece of human knowledge about the sun, including predictions of solar storms and technological safety, relies on signals sent from the past. The moment you look at the sun on a morning sky, what you see is not the present, but a trace slowly gathered from hundreds of thousands of years ago, plus the final 8 minutes and 20 seconds of its journey. And this delay opened a scientific revolution. If light cannot tell us what is happening inside the sun right now, what can? Beneath the darkness of the 400-kilometer-thick photosphere, where no light can pierce through to tell us what is happening below, something else travels outward: oscillations. Subtle vibrations of plasma ripple across the entire sun, echoing through every layer like the faint heartbeat of a living star. This is the realm of heliosismology, the science that studies the sun not through light, but through sound waves traveling through its interior. Heliosismology began to flourish at the end of the 20th century, when the first highly sensitive Doppler instruments on the sun detected that its surface is constantly rippling. With displacements of only a few dozen centimeters per second, these ripples are far too small for the human eye to detect, yet strong enough for observation systems like the Global Oscillation Network Group, SOHO/MDI, and SDO/HMI to capture with astonishing precision. For the first time, humanity could hear the sound of a star. These acoustic waves, called pressure modes, move throughout the sun's interior, reflecting millions of times as they carry information about temperature, density, rotation, and the physical properties of every plasma layer they traverse. By analyzing changes in oscillation frequencies, scientists constructed a three-dimensional map of the sun's interior, something light could never reveal. One of the most striking discoveries from heliosismology is that the sun's core rotates faster than its surface. Data from SOHO shows that the inner core, spanning roughly 20% of the sun's radius, spins 3 to 5 times faster than the plasma above it. This finding reshaped our understanding of stellar dynamics, revealing that energy and angular momentum stored deep inside the sun can influence the entire activity cycle of the star. But heliosismology does even more. It allows us to see deep circulation flows beneath the convection zone, moving at only a few meters per second, too slow for any direct measurement method to detect. These flows transport plasma and magnetic fields in loops that take decades to complete. And they play a crucial role in generating the Sun's 11-year cycle. Every magnetic storm, every sunspot, every CME may originate from these slow yet powerful motions. And in deciphering these flows, scientists discovered a mysterious region. The tachocline, the boundary between the chaotic convection zone above and the stable radiative zone below. Only about 0.04 solar radii thick, it is where rotation changes abruptly. Above it, the Sun rotates by latitude, with the equator spinning faster than the poles. Below it, rotation is nearly uniform. A star does not speak through light. Light tells us only about the surface. Its vibrations tell us about its soul. In each oscillation, the Sun sends a message. It is a living, changing entity with its own heartbeat and its own cycle. And understanding that heartbeat allows us to predict magnetic storms, interpret shifts in its magnetic field, and even protect modern technology from the wrath of space. As science began to realize that the Sun's personality evolves in cycles, Heliosismology opened the door to the next chapter of the story. The Sun transforming through every wavelength, every stage, every 11-year cycle. What we see with the naked eye is only one version of the star, a version at 5,700 Kelvin, golden, calm. The Sun, at its deepest essence, has a rhythm. A powerful, cyclical, and sometimes dangerous heartbeat that repeats roughly every 11 years. And this very cycle shapes the true personality of the star, at times serene, and at times erupting with a fury that Earth can never afford to ignore. The 11-year cycle is formed by the motion of the magnetic field inside the Sun, the very thing we touched upon when looking into the tachocline. In that region, differential rotation, where the equator spins faster than the poles, stretches magnetic field lines and twists them like taut cords ready to snap. When magnetic energy builds to its threshold, chaos rises. Sunspots appear in clusters, solar flares erupt, and CMEs blast into space. And when the cycle reaches its peak, the Sun flips its magnetic poles, as if exhaling after a period of intense strain, and then begins anew. What is strange is this: at each wavelength, the Sun appears as an entirely different entity. When viewed in the EUV 171 angstrom band, corresponding to plasma around 600,000 Kelvin. We see a delicate Sun draped in thin, web-like loops of plasma. repeating structures that are soft and intricate. But when shifting to a hotter wavelength such as 94 angstrom, corresponding to temperatures above 2 million Kelvin, jets of plasma burst straight from the surface, and active regions flare violently like massive wounds being torn open. The Sun's personality shifts dramatically as the 11-year cycle approaches its maximum. Data from NASA and NOAA show that during solar maximum, the number of sunspots can increase 5,100 times compared to minimum. These are not mere numbers, they are expressions of immense magnetic energy being unleashed, where twisted fields break apart and reconnect, producing explosions that can reach 20 million Kelvin in seconds. This explains why, every 11 years, Earth must prepare for a heightened risk of geomagnetic storms. The cycle also directly affects Earth's atmosphere. When solar activity intensifies, the ionosphere becomes more deeply ionized, disrupting radio communications. GPS accuracy, and high-altitude polar flights. CMEs can compress Earth's magnetosphere and induce electrical currents in power grids, as seen in the 1989 Quebec blackout that shut down an entire network in just 90 seconds. This shows that the Sun's temperament, even from 150 million kilometers away, can touch every layer of the technological world we rely on. During low activity, it appears relatively peaceful, few sunspots, fewer large magnetic loops. Yet, in high-activity phases, the surface becomes a turbulent canvas of massive dark patches, each one larger than Earth many times over. In soft X-rays, these regions blaze like natural reactors, where magnetic energy is released in rhythmic pulses. What's extraordinary is that although the average cycle is 11 years, the Sun does not follow a perfect rhythm. A cycle may last 9 years or stretch to 14, depending on fluctuations deep within its magnetic field. And it is this variability that fascinates solar physicists, especially as NASA predicts that cycle 25, the current one, is stronger than early forecasts suggested. This aligns with the unusually high activity seen during 2023 to 2024, when auroras appeared at much lower latitudes than normal. From million-degree plasma loops to the first human attempt to pierce through a colossal CME, to decoding why the corona burns hundreds of times hotter than the surface, and even listening to the heartbeat of the star itself. This journey has pushed past every physical and technological limit we thought we understood. Every stream of data, from the ancient 170,000-year-old light to the turbulence of solar cycle 25, now shaping conditions on Earth, reinforces one truth: we have only touched the outer shell of an immense, ever-moving, and endlessly surprising world. The total solar eclipse of 2024 is a reminder that even with giant telescopes and probes plunging straight into a plasma inferno, the sun still guards countless secrets beneath its photosphere, a realm modern science cannot yet reach, and the human eye can only glimpse the corona in rare, fleeting moments. But it is precisely these limits that keep the journey alive. The deeper we look, the more we understand that the star sustaining our existence is a cosmic engine far more complex and powerful than anything we ever predicted. And this is only the beginning of the many times humanity will look deeper into the sun in the future. A boundless scientific odyssey that challenges everything we think we know about the universe. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.